Well, before I just kind of alluded to the fact without explaining how to prove that if the dot product of two vectors is a constant, then the dot product of the vector and its derivative, that vector, is zero. I kind of alluded to it, but I didn't really give it a good explanation. Besides, I was talking about circles, if it's two dimensions, and it also applies for three. So let's see, how could we show that if this is the case, then the dot product of the derivative is zero, so we can clarify that thing I sort of mumbled over before. So that should be good for everyone, right?
Yay!
Oh, okay. Really good for everyone. All right, that's great. So if we just let our vector valued function be x of ti plus y of tj plus z of tk, then the dot product of that vector with itself equals a constant, could be written another way, x prime squared of t plus y prime, x squared of t, or maybe I should call it x of t squared plus y of t squared plus z of t squared equals a constant, which, I mean, I guess I was just assuming that they were linear, in which case, if they're linear, this would be, in fact, not a circle, but an ellipsoid. Okay, but if such dot product is a constant, then really an ellipsoid would be a good example of something like that. So if we differentiate both sides of this equation, this one, see, the right side, of course, comes out zero. The derivative of c is zero. The left side is twice x of t, then times the derivative of what's, the inside part from the chain rule, which is x prime of t. So we got 2x of t times x prime of t, and then we have the derivative of this part, which is 2y of t times y prime of t, again from the chain rule. And then the derivative of this part would be 2z of t times z prime of t. Again, the derivative of this is the chain rule, so that's where the z prime of t came from. And the derivative of c, as I said before, is zero. And so we have this expression when we differentiate both sides of this dot product. Recalling the dot product will give us not a vector, but a scalar function. So here's that scalar function, and when we take the derivative of it, we get this. Again, this is a scalar function's derivative, so it is 2. It too is a scalar function, and so therefore the left side of this expression here, believe it or not, is just the dot product of the vector r of t with the vector r prime of t. See, r prime of t would be x prime of t I, y prime of t j, z prime of t k. And so, actually, to tell you the truth, it's twice the dot product of r prime of t and r of t. But the whole point is, it's zero, right? I guess I could divide both sides by zero, and I'd have the dot product equals 0 over 2, but isn't that very cool? I should say twice the dot product of r of t and r prime of t. Hence, we've shown that the dot product of r and r prime of t is equal to 0. All right, don't you feel good about that?
Yay!
I knew you would.